This morning that we have about 150 registered attendees, and that's a record, I believe, for any U.S. AMOC science team meeting. And of those 150 registered, quite a few of them, I guess, from European registrants, and we have 68, if I'm not mistaken, in-person participants. That's more than what we originally anticipated, so I think that's really great. So what I wanted to do here is to present an overview of the U.S. AMOC science team. I'll be focusing on the accomplishments, but as well as the challenges, the remaining challenges, because by no means all the related problems or challenges have been resolved. So I've been serving as the AMOC Science Team Executive Committee Chair since about 2013. It's almost a permanent position. I took over from Bill Johns. And if I'm not mistaken, Susan here was the very first chair of the U.S. AMOC Science Team. So for those of you who are not familiar with what U.S. AMOC Science Team is, it's an interagency program. And it consists of all the proposals that are related to AMOC, and that decision or that distinction is made at the program manager level, and it is funded by the 4 agencies that are listed here. So what I wanted to do is provide a brief background of the science team, its history, objectives, and its organization. Then I'll mention a few of our recent activities. They'll be mostly legacy products that we were aiming for. Then I'll talk about, as I said, accomplishments and some challenges, and I'll finish with some thoughts on the future. And they are provided by Merrick from the observational side, and I have some additional thoughts at the end. And I wanted to right away mention that even though we label ourselves as the U.S. AMOC Science Team, we have really strong collaborations and partnerships with our international colleagues, and in particular with the UK RAPID program. And as Mike already indicated, the US AMOC Science Team was supposed to sunset in 2020, because of the pandemic. It got delayed to the first 2021, and then now we are definitely saying that it's going to sunset in 2022. And I just wanted to make sure that by sunsetting, we don't mean that any AMOC-related research is going to disappear. It's just going to be transferred, and we'll be doing additional sort of coordination activities that we'll be discussing later on throughout this meeting. So, US AMOC program, how it started. In January 2007, AMOC was identified as a near-term priority by the Joint Subcommittee on Ocean Science and Technology. And later that year, an AMOC implementation plan for the United States was released. And in March 2008, US AMOC Science Team was formed. And as I said, Susan was the very first chair of the science team. Since 2009, including this particular meeting, we had 7 national meetings, and we had 4 international meetings, and they were all in collaboration with the UK RAPID program. And the number that I'm quoting here is not necessarily an official number. I didn't get it from Mike. It's my own estimate based on previous AMOC reports. I'm estimating that over 200 AMOC-related projects have been supported by the 4 agencies that I mentioned earlier over the last decade and a bit. So that's quite a lot of projects. And I believe there are still 50-ish AMOC-related projects ongoing total. So what were the objectives of the US AMOC Science Team? When the science team started, there were 4 objectives, and they are given as the first 4 bullet items. Implementation and evaluation of AMOC observing system, assessment of AMOC state variability and change, assessment of AMOC variability mechanisms and predictability, and the final one was the assessment of the role of AMOC in global climate and ecosystems. Roughly in, I believe, 2017 or 2018 or so, we essentially started to focus more on the paleo-AMOC side, and there was a workshop in Wilbert, and subsequent to that, we added another objective to the AMOC science team, and that is the fostering cross-disciplinary collaborations among paleo scientists with the modern AMOC community. So that became the fifth objective of the US AMOC program. Our organizational structure pretty much reflects the objectives that I just mentioned. We have 5 task teams, and they are listed here, and their current leaderships are given here. The first names, or the person who's listed first is the chair, and then the second person is the vice chair. And together with these task teams, myself formed the executive committee, and as I said, I'm serving as the chair of that executive committee since about 2013. One of the, in my view, great things about the US AMOC program was the all-inclusiveness of all of the people who are working on AMOC-related projects funded by those 4 agencies. So it wasn't just the PIs, it wasn't just the co-PIs. We are all including all of the people who are associated with those projects, postdocs, students, or just friends of AMOC in that sense. That's what I call in general. So I think that was actually one of the main accomplishments of the US AMOC program. So in 2018, roughly, we were informed that the US AMOC program was going to be sunsetting. I know that, for example, Tom doesn't like the sunsetting word here because it feels like it is just ending the program. And I mean, he has a point there. I just wanted to again stress that the AMOC-related research will not just end because of the ending of the US AMOC science team. And in 2018, we were informed that it was going to be sunsetting, and then we, I think throughout our communications with the executive team and science team members, as well as our meeting, AMOC science team meeting, I think it was in 2019, we came up with, in a collective way, after discussions, what things that we wanted to finish or try to address before the sunsetting of the program and pass on to whatever comes next. And we came up with sort of categorized list of what we wanted to do in 2018 by the end of the program. And they were sort of divided into collaboration activities, priorities, what legacy products that we wanted to sort of produce, and finally, communication activities through websites and all that stuff. And I'm not going to go over all of the sort of bulleted items here, but I just wanted to highlight just a few of them over the next few slides. The point here is that we are trying to keep the momentum going beyond the completion or beyond the ending of the US AMOC science team. So that's one of our primary goals. As many of you know, we have been producing reports. They are not on a regular, initially they were about a year apart, but towards the end we made them more on the 2-year time scale. And our last report was published in 2018. It was supposed to be finalized with a final report in 2020, and that was one of our sort of goals. And because of the pandemic and delay of this meeting, that report is going to be now, the final report is going to be published in 2022. And I was told that Jenny is eager to finish it by the end of May. I'm just joking. So we are hoping to, because of the so many meetings that US Weijer is essentially going through and organizing, we are hoping that there will be a bit delay, but we want to publish the final report by the end of this year, certainly. And personally, and also I've heard it from others, that these reports are extremely useful because they provide a summary of each of the projects that are funded, like 1.5-page or 2-page summaries, and then we have sort of a list of what are the ongoing challenges and short-term priorities along with long-term priorities that are given in those reports. And one particular purpose of this meeting, through discussions and particularly through the breakout discussions that we are going to have on Thursday, come up with sort of an organized list of what the priorities should be going forward. And that's important because not just the community, but program managers pay attention to what's written in those reports. And I think it's important to get to put in really thoughtful and forward-looking items into what we need to accomplish going forward. That's important, and we need to come up with that list, hopefully by the end of this week. So one of our goals, or legacy products, was to produce an AGU virtual special issue. And we have done that. And the title of the virtual special issue is given here: Atlantic Meridional Overturning Circulation, Reviews of Observational and Modeling Advances. We have 9 published manuscripts, and they're not just single author or 2 author manuscripts. They are multiple author manuscripts, and you can see that there are US leads as well as leads from our international partners, particularly the UK RAPID program. And they have been published through sort of April 2019 all the way to January of 2022. And these should be all open access and publicly available. So early in 2021, about a year ago or so, Merrick, myself, and Mike wrote a commentary in JGR Oceans, introducing these special issue manuscripts, including, stressing the accomplishments as well as listing any, well, I shouldn't say any remaining challenges, listing the challenges that we thought of during writing of this commentary. So another thing that has been going on is the AMOC webinars. The webinars initially started, I think they were initially started by Task Team 3, and they were quite popular, and other task teams actually started participating in these webinars as well. So the last set of webinars that we have done are for the special issue manuscripts. Each of the leads of those manuscripts presented roughly a 20-minute presentation followed by 10-minute Q&A, and they have been listed here. I should also mention that even though Paleoclimate task team did not have a special issue manuscript, they are actually, it's my understanding, and Hallie can correct me, they are working on a manuscript summarizing Paleo-AMOC activities. And I think it's close to being submitted, right? Yeah. So, in effect, the last presentation here was a summary of that particular effort. All of these presentations are recorded. They are available from the US Climate Science Team website. We have live participants of over 1,055 people watched them live. But perhaps more impressive, after they are recorded, the total number of viewing of those recordings on YouTube today is over 4,500, and that's quite impressive, I believe. So it shows that there's significant interest in these presentations. And then another legacy product that we wanted to produce was participation in Oceanops 19, and there are 2 articles that was related or came out of science team activities. The first one is the observational one. It was led by Eleanor, and you can see quite an impressive list of co-authors listing the accomplishments and challenges. And then we also partnered with the International Clive Ocean Model Development Panel. There was an article on the modeling of ocean circulation models, or ocean circulation, modeling of ocean circulation. And there's a section there talking about representation of AMOC, challenges, biases, and all that, what needs to be done sort of in that particular manuscript as well. So that was sort of a sample of what we wanted to do, and I would say that we have accomplished already quite a few things that we said we would do prior to sunsetting of the AMOC science team. Now, I wanted to show you a few slides, sort of showing some accomplishments and highlights of the science team activities, starting with the rapid MOCA array. So This is, when I say we are collaborating internationally quite closely, this is one of the prime examples of perhaps one of the early examples of that collaboration. This is funded by NSF, NOAA, and UK NERC. The rapid array is across roughly 26.5 degrees north, and it provides observationally based estimates of both volume and heat transports across that trans-basin latitude. This slide, for the slides that I received from others, I always include a credit. This particular one is coming from Bill Jones. And this is also combining some of the comments sent to me by Merrick as well. So major findings are listed here. We have found out that there are large-term AMOC variabilities, even on a daily time scale. We have seen that AMOC had I don't know what you want to call it, either sharp or mild, depends, I guess, if you want to look at a longer time series, a downturn in roughly 2009, 2010 period right here. And this has obviously impacts on mid-latitude heat content. And after that sort of weakening or reduction in AMOC, since about 2010, AMOC stayed at a relatively lower state in comparison to the earlier period. And I mean, either you can interpret this thing, there were two different AMOC regimes, or one can just say that, I mean, if you actually squint your eye, maybe you can see that there's actually an increase in AMOC transport over the last decade or so. And there are also, we found out, well, from the observations, ocean meridional heat and freshwater transports are highly correlated with AMOC variability. Another observational program that started earlier than the RAPID program is the MOVE array located at 16 degrees north. MOVE stands for Meridional Overturning Variability Experiment. It is, in contrast with the RAPID array, MOVE is measuring the southward transport only on the western side of the basin. It is also below roughly 1,200 meters. It's intended to measure the southward flowing North Atlantic deep water associated with deep sort of return flow of the Atlantic overturning, and it's doing it in this region here. And it's to the west of the eastern part of the eastern mooring is to the west of the North Atlantic ridge. And this is literally hot off the press. Matthias just sent me this slide Saturday. I think it was Saturday. It's showing or Friday night actually. It is showing the most up-to-date version of the MOVE array transport estimate. The blue lines are, I believe, some 30-day averages, and then the red line shows decadal sort of trend estimate or decadal fit to that higher frequency transport. For those of you who are familiar with the MOVE transport time series available as of from their website, they'll notice that this transport is different. Matthias recently reprocessed the salinity, and I believe he's trying to account for the salinity drift in the MOVE array in a better way. He also adjusted the transport estimates from a 2005 cruise, so you'll see that there are large differences compared to the previous estimate here. So this is brand new results, and I believe Matthias, or I'm not sure, Uwe is going to talk about it later during this meeting. So one of the sort of interesting science questions was, well, do the RAPID and MOVE estimates in their trends agree with each other? So in 2018, Eleanor led a manuscript just focusing on the observations, looking at comparing the MOVE and RAPID trends. So for the common period, black line here is the RAPID time series, and the red is from the MOVE array. So if you look at their trends from 2004 to 2015 period, while rapid indicates about a 4 square root of decline of AMOC, move array is actually showing an 8 square root of per decade increase of AMOC. And in that observational manuscript, Eleanor and co-authors attributed these differences primarily to the calculation of the compensating flow in the rapid. And depending upon how you calculate that transport, and I'll show you an example from the modeling world as well, it can change your trends quite significantly. Of course, the calculation of the reference depth is also important, and you can get different trend results depending upon how you account for that reference depth and velocity. So from the modeling world, as part of our AMOC metrics project, we try to provide an apples-to-apples comparisons of these of the transport at these sites using different model estimates of the velocities or transports, including the transport estimate as close to the observational method as possible. And what is shown on the right side is 5-year, 10-year, and 30-year trends. The orange line is from move. The blue line is from the rapid. So as you go to lower frequencies or lower frequencies or longer periods, you can see that the trends in both areas agree with each other. But there are some disagreements at 5 and 10-year time scales. So what I'm also highlighting on that on those plots is the compensating flow for the rapid. That's the volume compensation. It is constant across the transect, but it changes in time. You can see the gray line, and the total transport is the blue. Gray is much larger than the total transport, indicating that interior and barotropic transport, in a sense, are two large components, and you're subtracting or adding them together with opposite signs, you end up getting with smaller magnitude trend. But how you compute and account for that compensating flow makes a huge difference, or can make a big difference. So from modeling work, we also computed the trends for the observational period 2004-2015, using different methods from the model as well as the observational method. You can see that the rapid and move trends tend to agree with each other in the modeling world. They're also, the models are saying that move and rapid actually show a decline of AMOC of 0.2 square roots per decade. So another, this is more recent than rapid and move, major observational program is the overturning in the subpolar North Atlantic, OSNAP, and I think Susan is going to be talking about right after my presentation here. And I don't want to spend too much time on this, but one of the major, so the OSNAP area is at these high latitudes. I can't show it. It is measuring the transport estimates or providing transport estimates on the western side and as well as the eastern side. And one of the, so this time series is for 4 years. The total transport east plus west is shown as the black line here. And then the individual east and west sides are shown by red and blue lines here. So one of the major outcomes of this observational program so far, or major results, is that OSNAP East is the primary sort of dominant contributor to AMOC variability or overturning variability. In comparison to the west side, you can see that that's the case for both the mean and variability, and this is in contrast with many, if not all, modeling results. They show that Labrador Sea, in particular, is the dominant contributor to the AMOC variability. So needless to say, I think this was first introduced in 2019 US AMOC meeting, and it created a lot of stir. And since then, there have been many manuscripts coming out. So one of them was again co-authored by Susan. It shows that Iceland and Urbanger basins are contributing, are the primary contributors to the variability. And this was from observations. then you can see that, I mean, I'm not listing all of the manuscripts. Lots of manuscripts came out. Another one was Matt Menery, and they tried to reconcile the results from observations and models. And their finding is sort of the second bullet here. The model demonstrated a link between AMOC and lab C densities consistent with previous modeling based results. Then another recent one was led by Dylan, and they showed that despite they showed that the Labrador Sea is playing a role. This is a modeling result. And another recent one that I was led by Steve Yeager here with a bunch of co-authors. And I'm showing the results from that particular manuscript. The top panel shows the mean water mass transport, water mass formation, and meridional overturning at OSNAP site. And the bottom panels show the low-pass versions of the standard deviation of the same fields. These are from high resolution forced ocean simulations. The primary point is that the models do agree in the mean and short time scales that the west is perhaps important, western side. But water mass, if one looks at the water mass formation, Labrador Sea actually shows up in the model as one of the primary sites impacting AMOC mean and variability, particularly on longer time scales. So if you look at the OSNAP transports with low-pass filtering, 10-year water filter, I think, at long time scales and low frequencies, you can see that the Labrador Sea is dominating. So perhaps we need to go beyond, obviously, 4 years to get a more concrete comparison of the models and observations. And I believe Susan is going to probably touch on this topic as well. The final observational product that I wanted to quickly mention is the, SAMBA. And SAMBA is located at 34.5 degrees south, and it is providing observational transport estimates since 2013 or so. So I wanted to briefly touch on AMOC in reanalysis products as well, because it's an important component of our AMOC science team. What I'm showing here is 6 AMOC mean distributions from 6 reanalysis products in comparison to a forward model. This is from Kaspek et al., and the means are over 1960 and 2007. Another recent paper by Laura Jackson looked at 11 reanalysis products, and they considered only the more recent period where the observations were more available, 1993 to 2010. So you can clearly see that there are differences in the AMOC mean estimate in reanalysis products. One can argue perhaps that if you ingest more observations, you tend to get better agreement on observations. And I think although some of the observations products still are the same, regardless of which period you look at, ECDA is the same in both, whether you look at the recent period or the more longer period. And in terms of their representation of variability, you can see this is from 1960 to 2010, AMOC time series at 45 north and 26.5 degrees north. This is for the more recent period. There is not much agreement in the longer period, but perhaps one can argue, as done in Jackson et al. Paper, that there is more agreement during the recent paper among reanalysis products, but that's still a bit murky to me. That's my personal opinion. So just to try to finish up, we have seen what we learned over the sort of decade or so. We have learned that there are many influences of winds in AMOC mean and variability, and that is becoming much more clearer as indicated in this slide. For example, mid-latitude winds dominate AMOC variability from seasonal to infrannual timescales, leading to mechanisms for upper ocean heat storage, for example. And our task team, number 4, worked on AMOC interactions and how they essentially impact many things: surface ocean state, global atmospheric circulation, and so cryosphere. And our last task team, they've also indicated that there have been some recent things we have learned about AMOC from the paleo world, and some of them are listed here, such as the Pacific Arctic sector, maybe more important than we thought for abrupt changes. Simulated AMOC is potentially biased towards a monostable state, Glacial AMOC was definitely shallow, changing global overturning circulation, and Henrik events are not all the same. So now I'll finish with some thoughts. This is from Merrick. Observing the AMOC, the future. According to him, observing the AMOC, determining its meridional coherence, how it is changing over long time scales, and the consequent impacts continue to be a challenging problem. In addition to in situ observations, satellite observations can contribute, and they are listed here. And the overarching challenge is to build a sustained AMOC observing system that's probably financially affordable as well. And then these are some of my thoughts. Many unresolved issues clearly remain. AMOC-related research will continue after the science theme sunsets. Important elements of the science theme, I believe, should continue to include sustained observations, collaborations, coordination, and communication at both national and international levels. I think it's important to keep the efforts focused and identify emerging future research directions. And moving forward, we need to move towards tight coordination of observational, modeling, and data assimilation efforts towards more process-based understanding. And finally, I just wanted to mention that we have formed an AMOC task team under the Weijer Atlantic Regional Panel to coordinate and continue some aspects of AMOC-related efforts, and we'll be discussing this more, I believe, on Thursday. I think Eleanor is going to present what's going on here. And with that, I'll stop and take questions, or I don't know whether we have time for questions.
I think we have time for a couple questions.
And that's a joke at the end. I don't know whether some people... AMOC is equal to sliced bread. When I was actually testing the website for this meeting, they asked me to be the guinea pig, and I didn't come up with any other title, and I just said AMOC is better than sliced bread. Some people noticed that they kept asking me those questions, so that's good for those people.
All right, thank you, Gokhan. We have time for one question. Anyone in the room or online have any questions? For those in the room, we have 70 people online.
Everything was so clear.
Very clear. All right, I think we should move on. I'm going to hand this mic off to Mike Hall, who can introduce the next speaker.
Thank you. Thanks, Gokhan. Our next speaker is Susan Lozier, and she's going to be talking about OSNAP.
Thank you, Gokhan, for that introduction, but also thank you for your leadership over these many years. Appreciate it. Mike and I were talking at the beginning that the two of us were on the implementation panel back in 2007. I do want to know that I was involved in the first US AMOC share when the program was growing and initiated, and here you are shutting it down, but I thought you would appreciate that I noted that. So, we're starting with the summary, which I don't mean to, so.
It keeps moving itself.
Gokhan gave a quick introduction of OSNAP, but I do want to make sure that everybody knows I'm up here talking about OSNAP, but OSNAP is an international collaboration with oceanographers from the US, Canada, UK, Germany, Netherlands, France, and China over these many years since we initiated the OSNAP program. So I'm very pleased to sort of give a very quick 10 to 12 minute overview of this program. And I really need to acknowledge here in the US that our funding agency has been NSF. And really, in particular, I want to give a shout out to our now retired program manager, Greg, who's really very supportive of the program from the beginning. So just for those of you who don't think about OSNAP every day, just want to give you a quick look at the cross-section here. This is the salinity, and just in general, the overturning in the subpolar North Atlantic involves warm, salty waters, the North Atlantic current moving northward. That's where you see the strong salinity signature there in the orange and yellows. Those waters are converted in the Erminger, Iceland, also in the Nordic Seas and in the Labrador Basin to produce the homogeneous water masses you see. They're actually a pointer, right?
It's the mouse.
Oh, the mouse. Okay. There we go. Those waters then are overturned to produce the convective water masses we see in the Erminger Basin and the Labrador Basin as well, and then we also see signatures of the overflow waters as well, and those are contributing as well to the overturning circulation. As Gokhan mentioned, our
You click on it.
Thank you. Third time's a charm. In 2019, we produced a 2-year time series. In 2021 was a 4-year time series, and this is a 6-year time series. Yao Fu, who is here at the meeting, is lead author on the paper. We hope to submit this soon. And also, he's talking about the seasonality in AMOC, MHT, and MFT. As Gokhan, and the 6-year time series shows us pretty much what we've been seeing in the 2-year and 4-year time series, that OSNAP East dominates in the mean and dominates in the variability over OSNAP West. The two questions that this time, when we first got the time series, the two questions that came up: why is the overturning Labrador Sea so small, and what is responsible for the overturning across OSNAP East? So I'm going to give a brief overview of those two. We can look at the overturning in density space, which we just talked about, but you can also look at the overturning in temperature space and in salinity space. So when we focused our attention on the Labrador Sea and we looked at the overturning in temperature and salinity space separately, we found that in temperature space, the overturning was 13.9 spherodops, meaning 13.9 spherodops of water converted, warm water converted to cold. And then in salinity space, 11.4 spherodops of salty water was converted to fresh. So obviously, one of our major conclusions from this paper was that there was a strong degree of density compensation going on in the Labrador Sea, such that the overturning in density space was quite small. Recognizing that this work was restricted to just a 2 or 4-year time series, we worked using a reanalysis product, Lozier 5, to see if this held over a longer time period, over the 26 years of this reanalysis product. And what you see in blue and red are the overturning in temperature and salinity states, respectively. And then you see the much reduced overturning in density space here in the Labrador Basin from this one reanalysis product. Of course, the question is, what is the mechanism that is producing that density overturning? And very particular here. There we go. It's just, I think it's just stuck. So postdoc Yana Maviva has been working with me now and trying to understand the mechanism. And so what she has done is she has taken the 2D model that Yana developed in 2006, primarily the Labrador Sea, and we've added a third layer. So we have the ocean interior, we have the boundary current, and we have the coastal waters that are rimming the Labrador Sea. And we're looking at trying to understand, as the boundary current moves along the path, how the impact of the surface forcing and the input of those coastal waters providing relatively fresh water is impacting the density compensation. So on the right here, what you're seeing is in the red along the path, so starting at the West Greenland current array going to the array off the Labrador coast. This is the path length. What you see then is that the salinity contribution to density is acting to lighten the waters, all the while the cooling is acting to densify the waters, such that along the path, black, there's very little change in the density. And so overall, what we find is that the cooling in the boundary current itself is being offset by the input, the mixing of those fresh coastal waters all along the path into the boundary current.
You can use the mouse.
I tried to use, yeah. Here we go. The second question I'll address then has to do with OSNAP East. So just with OPROC in the Labrador Sea, we found a surprisingly small overturning, but then we were saying, well, why is it so large across OSNAP East. So on the left, shortly before our first OSNAP time series came out, there was a publication by Bring It Out et al. Looking at this 20-something or almost 20-something year time series of the transport of the overflow waters of the Barrow-Bainland Channel overflow and the Dimmock Strait overflow. And what you see is, first of all, in the mean, it's relatively small compared to what we were seeing at OSNAP East, but also what I really want to point out is that the variability of that, of those overflows is very small compared to the variability we're seeing across OSNAP East. So on the right, in the paper led by Tillis Petit, in 2020, what you see in magenta is the Greenland-Scotland Ridge overflow waters, and then the difference between the OSNAP East, so OSNAP East is in black, and then when we subtracted the overflow waters, what you see is that dark blue line. And what that says is that in the Irminger and Iceland basins, that distance between OSNAP East and Greenland-Scotland Ridge, there's really strong variability. And what's creating that strong variability and that strong mean then, particularly really so strange not being able to do this. I think she can't push a button. There we go. It just takes off. Okay, so what's responsible for that? So as part of that study, what Tillis did was we looked at the transformation of the waters. So we're using the surface buoyancy forcing from Arrow 5 and INSTEP. On the left, we looked at the transformation to sigma MOC, which is across the east, 27.55. And then on the right, what we did, we took the measurements from the Greenland-Scotland Ridge, our OSNAP East measurements, and essentially did a volume budget. So what you're seeing there in the red, we're looking at how much water is going northward across OSNAP East, and then northward across the Greenland-Scotland Ridge, and we surmised that we were losing 7.6 faradays to the lower layer. And then we did the same thing to the lower limb. We have coming across the ridge, those blue numbers, which is about 6.6 faradays. And then we looked at how much was moving across OSNAP East, and so we surmised that we had to gain 6.6 faradays from the surface. So those numbers were within air of each other, and nicely, the transformation there in black provided that 7 faradays. And so we were able to, in the mean, show that by and large, the surface transformation is responsible for that divergence of those waters we see across OSNAP East. I'm going to break it here. Jenny, maybe you can help me. Oh, see, just have to bang it. Okay, so that again was using the observation. So we went back to 4 different reanalysis products that you can see here. And we're asking the same thing. Can we, across OSNAP East, account for the production of water masses and that divergence, that net outflow across OSNAP East by the surface transformation? So you should pay attention to the black lines and the red lines. In the black line is the transformation, and in the red is the divergence, meaning OSNAP East minus what we've gotten across the Greenland-Scotland Ridge. So we're really looking for those waters that are produced between OSNAP East and Greenland-Scotland Ridge. So in the mean, those black and red lines agree within or less than a faraday. But you can see that there's a storage term, that's the DDT in gray, and then there's also a residual. So there is likely mixing going on, but the main takeaway is that we really do have a balance, at least from these 4 reanalysis products, between the surface transformation and that net outflow across the OSNAP East. So, it looks like advanced. There we go.
Anytime I come close.
I know, that's it. Stay there, Jenny. It's so embarrassing. Can you come push this button for me? Okay, this will be very quick, and I'd love to talk to you about it again. We are really interested in understanding now how we can optimize the OSNAP array. So this work is just started. We're looking at what part of the array do we need for OSNAP West and OSNAP East in order to capture the variability of MOC, MHD, and MST. We're looking at two different analysis products here. These are OSSI experiments, so we know what the model truth is. And what you're looking at here, moving both for west and for east, we are first at the very western part of the array, we're taking the time variable part of the temperature, salinity, and velocity field. And then as we move across, use time varying to begin with, climatological monthly means elsewhere. And then we just keep marching across and adding in the time varying field. So by the time we get to the easternmost point of the array, whether it's west or east, we should have a correlation of 1. So by doing these experiments, and there's many more to come, the takeaways are that for OSNAP West, we really need those boundary arrays to capture the full variability in MOC, MST, and MHT. Read Sylvia Lee's latest paper to understand why. In the east, we can fairly well capture the array AMOC, but to really capture both MHT and MST, we really need to capture that variability in the NAC. Happy to talk to people about that later. I'm going to summarize now. Thank you.
Closer.
Closer. Quickly then, I mentioned the first one, I talked about the density compensation. Idealized modeling suggests that this compensation is due to the offset of surface cooling by the input of fresh coastal waters. Major contributor to the overturning is in the Erminger and ice basins. Strong interannual variability is a result of the storage, likely a result of strong wind forcing in the subpolar North Atlantic. I didn't get a chance to talk about it, but Gokhan showed our OSNAP Floats program. I talked about it in Ocean Sciences. We'll be talking about the OSNAP Floats program as well at ETU next month. But the main result from there is that the spread of ISOW and DSOW are remarkably different. I mentioned the study of the OSNAP optimization is ongoing. Anomalies in a single boundary current do not capture a meaningful amount of AMOC variability, particularly in the Labrador Sea. This was also highlighted in a recent paper. The link between convection and interior boundary current anomalies is not straightforward, at least on the timescales of the OSNAP time series. Last point I want to make here before I get to what we don't know, the transformation of surface waters on the surface outcrop and boundary forcing. Tillis' 2021 paper suggested that a large, the former, meaning the outcrop area, plays a larger role in the variability and buoyancy forcing in creating variability in that transformation. Okay, what we don't know, the title really should have been what I don't know. All of you know this. You see me at break. So is the feature of that time series representative, of MOC, MHT, MST, variability on longer time scales? We appreciate that the NCAR model there has said that on longer time scales, the Labrador Sea variability may play an important role. I do think, though, given the spread of models that we see, the model results that we see, it's really important to see those results in a number of models rather than in a single model. I'm also really interested in understanding how that could be on the longer time scales. Given the role of density compensation really drastically reducing the overturning in the Labrador Sea, I think there's a big open question about how ice and glacier melt will impact overturning in the subpolar North Atlantic in the years and decades ahead. Really interested in what its differential impact might be in east and west. Not sure how quickly the deep water formation variability in the Labrador, Erminger, and ice basins will be communicated downstream. We really can't see any connection with the rapid time series to date. Big open question is how will changes in the impact uptake and in CO2, and why is there still such a spread in the AMOC response among climate models, ocean models, and reanalysis products? Thank you. And I think we went over time, so step button, please.
You're good on time.
I'm good on time.
We started early.
Awesome. Okay.
So I think we have time for one question. And do remember that after this whole session, we'll have a 45-minute discussion. Question from Wilbert?
I guess
still trying to understand what then the role is of deep convection compared to more gradual transformations in boundary layers. Is that something that you have gained more insight in?
You're saying, what is the role of to the total overturning, convection in interior, compared to the role in the boundary currents themselves?
Correct.
Yeah, so we did focus on that in the 2021 paper, Billy Lee's paper, where we looked at the relationship between the anomalies in the interior and the anomalies, the density anomalies in the boundary current. So I'm not sure if that's what you're asking.
I'll take another look at the paper.
Okay, thank you. I'm happy to talk to you at break as well.
Okay, thank you. Our next speaker is Leah Chomiak, and she's going to talk about targeted effective timescales for overturning pathways.
She's making the button work now. Just so you know.
Okay.
She just tabled it for my
Morning, everyone. My name is Leah Chomiak, and kind of to segue off this one, let's do some big questions of how quickly we can see these signals communicated to the lower latitudes. That was the motivation of my work here, inferring effective timescales and overturning pathways of the deep western boundary current in the North Atlantic through the advection of Labrador seawater. So I'm from the University of Miami. I work in partnership with Alamos. I'd like to acknowledge my collaborators here, also from the Bedford Institute in Canada. Okay, sorry. So to start, the deep western boundary current, as we know, is one of the major transporters of all newly formed North Atlantic deep water, and is one of the major driving forces of AMOC. It's monitored, as we've been discussing, through numerous observing platforms that measure its current transport and its variability. And so these deep waters that are formed in the subpolar North Atlantic are especially important because we can use them as effective tracers due to their known water mass properties. So previous studies have focused on looking at general circulation and modeling outputs that estimated about a 4-year transit time to go from the subpolar region to the tropics via the deep western boundary current. Alternatively, the vector tracer studies estimated approximately 8 to 10 year transit time to reach 26.5 north and about 20 years to reach the equator. But albeit all of these studies basically do not come to a conclusion about effective timescales and overturning pathways within the North Atlantic. So in this study, we characterized deep western boundary current convection by tracking Labrador seawater effective signals to the tropical Atlantic via their unique temperature, salinity, and density signatures. So to do that, we employed the 4 different hydrographic time series, as shown here in the schematic, with our source region data set being hydrographic observations in the Labrador Sea, starting from the year 1970. And so the classically understood deep western boundary current pathway, one that flows along the continental shelf, is sketched here as this big black line. So we employ use of the Line W hydrographic program, as well as the Abajo 26.5 North program to monitor the advection across the current here. And then one of our secondary goals for this project, we seek to gain insight to the hypothesized alternate effective interior pathway. So to do that, we employ use of looking at Bermuda hydrographic data from the BACT program. Okay, so one of the first challenges upon entering this project was defining Labrador seawater. And so previous studies have defined it in a multitude of ways, as described here. But the takeaway is that these previous definitions are inconsistent when you look across a vast geographical domain, where the scope of water that's defined by one boundary is not containing the waters of a boundary further south, as represented here in the schematic here. So I just show previous definitions from other studies that have looked solely at the advection of Labrador seawater across the deep western current. But basically show that the different layering or classifications rather vary upon these different studies and can be biased based on the local parameters or just of observing bias. And so what we introduced in this study are the new method of identifying laboratory water through a neutral density framework. So using neutral density as opposed to sigma 2 or another method, because with neutral density and its computation of geography in it, gives us the best method to trace this throughout the North Atlantic. And so we divide into intermediate, deep, and vessel layers, where the intermediate layer is the focus of this study as it constrains all laboratory water classes based on the historical records. And laboratory seawater is denoted by a minimum in temperature, minimum in salinity, and also minimum in potential vorticity. So it's shown here in these TS diagrams. This intermediate layer is shown as the shaded region here, highlighting the minimum in temperature and salinity, as well as supported here through the minimum in potential vorticity. And then on the far left, I just showed schematics of these different layer boundaries and neutral density, but showing their depth within the water column at all 4 locations. To start looking in the laboratory, as this is the source of all of our convective signals, there's been multiple convective events, just looking straight from the 1970s here. We have a convective event in the 70s into the late, and then in the late 80s into the 90s, or again in the 2000s, and then more recently in the later 2010s. However, this convective event from the 80s, 90s period was the most prominent, producing the coldest, freshest, densest, deepest layer, and most voluminous louder seawater layer within the historical record. So using these convective signals as advanced tracers, we employ these 3 different methods to kind of gain convective estimates via the deep western mountain current. Our first method is looking within the defined intermediate layer across all 4 locations, where essentially we're taking a vertical average of this layer to characterize the effective timescale based on the arrival of the minima in both temperature and salinity. Next method is diving deeper within this layer, highlighting 2 individual lager seawater cores, the core of the 90s class, and then the shallower layer class of the 2000s. And then as a third, more quantitative method, we focus on the cross correlations of both the layer and these cores of all time periods to that of the laboratory. So to highlight the first method here, so again, the entire intermediate layer across all 4 locations, where we vertically average within that defined neutral density bound to create time series of temperature and salinity. And based on the arrival of minimum, we can gauge effective timescales. And so based on the original minima in 1994 of the laboratory, we can then conclude that there's an effective lag of about 3 years to reach line W, and then very similar effective lag between Bermuda and AMOC, where we have a still minima in both potential temperature and salinity, but they are flip-flopped based on Bermuda and AMOC. And so the results here are kind of varied and ambiguous. Why is water reaching Bermuda and AMOC at the same time? This is weird. This is leading into the next method of where we identify these 2 laboratory water classes individually. So the core of the 90s is deeper, as I said, and along a heavier exotignal. That's shown here by the yellow arrow. And then we have our laboratory water class of the 2000s, which is lighter and shallower, shown as the red. Then here I'm showing anomalies of potential temperature and salinity across all 4 locations, where we can visually see the onset of these 2 water masses propagating through all 4 locations. So if we take the isothermal layers of each identified laboratory water core, we can again plot the temperature and salinity along all 4 locations of both water masses, and then use the minimum of this signal to gauge effective timescales. So shown on the left over here are the effective estimates here, timescale estimates, where an interesting find is that the laboratory seawater class of the 2000s is shown to attack on a longer timescale, taking about 7 years to reach line W, and timescales on the order of 12 to 14 to reach Bermuda, and similarly also to as well. Okay, and then as the third, more quantitative method, we perform cross-correlation analyses of each time series to that of the laboratory. deep, to try to gain an effective lag estimate. And so we do this both for the two individual lateral seawater cores, as I've mentioned, as well as for the intermediate layer itself. So the top figure is showing the correlations of the two cores, the lateral seawater core of the 90s, is shown in the more shaded coloring, and the core of the 2000s in the lighter shaded. And you can see right off the bat that the core of the 90s is at the sugar rate as opposed to that of the 2000s. And again, this is also supported when you look within the layer. So shown at the bottom here, might be a little hard to figure out, but we're showing the entire intermediate layer, but broken into an upper and a lower half that more hones in on the two respective lateral seawater classes. So on the left side is the lower half of the intermediate layer, highlighting the core of the lateral seawater class of the 90s, shown as the black line there. And then on the left, to the right, is the upper, highlighting the core of the 2000s. And again, we can see that the lateral seawater class of the 2000s is presenting at a longer time scale than that of the 90s. But most notably, we're seeing that both signals of both cores are reaching Bermuda at the same time or just prior to that of reaching AMOC. So based on the study, or the evidence from this study, based on the evidence presented in this study, we can kind of verify that there is indeed some sort of interior pathway that's bringing these signals to Bermuda, which is outside of our classically understood deep-water current effective pathway, and having them be seen at Bermuda just prior to around the same time scale as AMOC. So to dive a little deeper, we look within these deeper layers. So shown here are just the geostrophic velocities that were derived from Argo and altimetry measurements, both at reference depths of 1,000 meters, but also at 1,500, 1,750, and 2,000 meters, which is more representative of the layer that I'm working with here. And we can see right off the bat that there is this interior recirculation pathway that is shown via these velocities, where water is bifurcated off the coast of Cape Hatteras, likely from a Gulf Stream influence, I had to guess. But this water is being circulated into the interior, making turns at approximately 56 to 50 west, passing Bermuda in the process and rejoining the continental slope at around 30 degrees north. So this is one possible mechanism of why we're seeing these signals reach Bermuda prior to reaching AMOC or on similar timescales. Because there's also that similar timescale notion, it's very difficult to determine if a deep western boundary current southward through flow pathway is present south of 36 north due to limitation in Argo, but it's very likely that there is a leakage there. And so the different effective pathways that we see here likely explain why we have varying effective timescale estimates from the study. To quickly conclude. So first, we were challenged by the notion of defining lateral seawater and basically reinvented a way of providing all-encompassing definitions that are suited across a wide geographical range. Second, we also identified two distinct lateral seawater classes among all time series. And through that, we were able to estimate the effective timescales of the deep western boundary current through the 3D methods described. And most notably was seeing the arrival of the lateral seawater signal at Bermuda just prior to around the similar timescales to that of AMOC, which offer a contrary route of the deep western boundary current effective pathway. And this was supported through the hydrographic data presented as well as the adjusted geostrophic velocity. So with that, you. Great, thank you, Leah. Any questions? One.
Hi, David Connelly, yeah, thanks for that talk. I was just wondering, downstream, I guess the Labrador seawater at, say, line W or further south, it's not going to be 100% Labrador seawater, it'll be trained quite a lot. So when you kind of account for the timing, how do you account for if you've got variability in the properties of the other water masses that could, like, patient.
Great question, and I have only so much time to explain how I did all this, but, in my paper that's hopefully being submitted very soon. So we did a lot of processing to the hydrographic data, because there is obviously an entrainment, as you described. And we do see a huge property shift in the temperature and salinity, basically from the level C to upon arriving at line W. It suggests that there's a lot of sunset happening between those 2 points. And so a lot of the influence, which has already been looked at in previous studies that AMOC today, show a large influence of Mediterranean coastal water mixing in, which occupies a similar density level, but is warmer and saltier, which changes the parameters. So part of the hydrographic data processing was removing the Mediterranean signal, which there was a method that we used to do so, and estimated about like 15% of profiles removed from line W, just based on the criteria that we used, and about 20% from Abaco, and about close to 50% from Bermuda, which obviously had a larger influence. But yes, that was a big challenge to also trying to hone in on this convection signal. Yeah. All right, I think at this time we'll go over to the poster session.
Yeah, so the first poster session is virtual, and I think there's some coffee and tea for break. We're going to reconvene here and online at 11 o'clock.
So, yeah, for those who...
All right, good morning, everybody. I'm going to talk about the coupling between the Arctic and the Atlantic Meridional overturning circulation. And this is the list of co-authors that you can see here. And basically, we've been asked to to provide a review paper for a special issue of oceanography on the new Arctic Ocean. Several papers have already been published, and this is the link where you can look at those papers. So you can ask to write a review paper on recent advances in our understanding of interactions between the Arctic and the AMOC. And this is supposed to be for a general audience, so it's not comprehensive, and everything that I'm telling you in the next 10 minutes is, you probably already know that, but at least for me, it's been really good experience to put everything together and to really dive deeply into the literature. And also, of course, in the 10 minutes, I really can't do anything more than just briefly glance over the literature and address some of the papers that I think are very relevant, most relevant for this for the topic. Anyways, first linking the AMOC and the Arctic. So this is a schematic indicating the regional area that we're talking about and main circulation features. And of course, we have the subtropical North Atlantic, the subpolar North Atlantic, and the Nordic Sea, and the Arctic Ocean. And they're separated by a couple of gateways. The Greenland-Scotland Bridge connecting Greenland and Scotland through Iceland and the Faroe, the Barents Sea opening, French Strait, and the Davis Strait. There have been some estimates of the transports across these gateways by Östros, for instance, in 2019. And to aggregate them, they suggest that there's about 8 shredder of Atlantic water going north across the Greenland-Scotland Bridge into the Nordic Seas. About 6 shredder going south on the deeper level of the overflow water. 2 shredder going south as polar water, which is cold but relatively fresh and for lighter. And also 2 shredder southward transport through Davis Strait. I added some values from Subuchi, some estimates from Subuchi et al. 2018 on the transports through the French Strait and the Barents Sea opening, suggesting about 5 shredder of Atlantic water going into the Arctic, and 2 shredders going south as the deep waters, and 2 shredders going south as the relatively fresh polar water. So you can make an estimate of the overturning circulation, overturning cells, and it's very convenient to have this double estuarine model of the Arctic in mind. So it consists of a thermohaline cell, in which Atlantic water is converted to dense overflow water, and an estuarine cell, in which Atlantic water is converted to relatively fresh polar water. And this schematic would tell you that there's a thermohaline cell of about 6 shredders in the Arctic, consisting of both the Nordic Seas and the Arctic Ocean, and 2 shredders of which is converted in the Arctic Ocean and force further in the Nordic Sea. And there's an estuarine cell about 3 swirls. And I'll get back to this little estuarine model in a couple of slides. How much of the inflow into the Nordic Seas is of subtropical origins? And I think this Schmittner paper is very insightful in that. They basically argue that the subpolar gyre modulates the salinity of the eastern North Atlantic. And it's kind of a switch arc between subpolar water and subtropical water, with a strong gyre indicating a relatively fresh eastern North Atlantic consisting mostly of subpolar water, and with a weak gyre indicating relatively salty eastern North Atlantic consisting mostly of subtropical water. This figure from Kuhl et al., analysis from Kuhl et al., suggests that there might be between 50 and 70% of the waters in the eastern North Atlantic might be of subtropical origins, depending on the strength of the subpolar gyre. So how will this connection change in the warming climate? Well, I think several studies have indicated that the AMOC is projected to reach further into the Arctic. A northward shift of deep convection, for instance, was suggested by this modeling study by Leah and Alamos, but also Bits et al. In 2006 already indicated that the overturning circulation may reach much deeper into the Arctic. So this suggests that there might be a stronger link between the Arctic and the Atlantic meridional overturning circulation in the future, even though the AMOC is projected to weaken. AMOC impacts on the Arctic. So of course, one of the main things about the overturning circulation is that it transports a lot of heat northward. This estimate from Schmittner et al. 2022, a recent review paper, suggesting that about more than half of the heat transport across the Greenland Scotland ridge is accomplished by the overturning circulation. So it definitely plays a very important role in the heat budget of the Arctic. And it also shows like a trend, a multi-decadal trend, especially in the last couple of decades, which was addressed by Lozier in their 2021 paper. They argued that there is an increase of Atlantic water inflow, but also higher temperatures of this Atlantic water that led to this increase in heat transport in the early 2000s. And that's despite the weakening of the AMOC in 26 North, as was inferred from the AMOC array at the 26 North. So they basically argued that there is a discontinuity between the AMOC, the strength of the AMOC at lower latitudes, and ocean heat transport into the Arctic. And I think this is something that has been confirmed by many other studies, that there is not a one-to-one correspondence between AMOC strength at lower latitudes and the ocean heat transport into the Arctic and towards the Arctic Ocean. That said, there is several studies that look at the heat content anomalies that can be traced from the subpolar North Atlantic, maybe even the subtropical North Atlantic, into the Nordic Sea. Steve Weijer and Orton et al. 2017 have made a case for that. And they argue that this is a kind of a potential source of predictability for the high latitude Earth systems in Arctic Sea, in particular, the Barents Sea and Barents Sea. Many ways that the Arctic can impact the AMOC. So and Arctic plays an important role for the overturning circulation. One way is through the one-mass transformation. And here is where the double estuarine model comes back. Tom Haynes published a paper last year with a very schematic representation of the Arctic that captures the main ingredients of this double estuarine circulation. So it consists of Atlantic of the estuarine cell, in which Atlantic water gets cooled and freshened and leaves the Arctic as polar water, as well as the thermohaline cell, in which the Atlantic water gets mixed with shelf water, salty shelf waters, and leaves the Arctic as overflow. That is this transformation in TS space, T and S space, where you see that the temperature drops considerably, but the salinity doesn't really change a lot. Tom Haynes argues, based on the analysis of that model, that the thermal cell, the thermohaline cell, is robust, but the estuarine cell is vulnerable to a heat crisis, which the model cannot no longer satisfy the heat budget based on these two overturning cells. And that in this case, the estuarine cell might disappear when the amount of heat imported by the Atlantic water gets stronger, or when there's an increase in the stratification due to increased meteoric freshwater flow. And he also argues that the acidification that has been observed in the last decade might already be a precursor to that heat rise. Of course, another way that the Arctic impacts the AMOC is through freshwater inputs. AMOC is thought to be sensitive to these freshwater inputs, mainly through the freshwater capping that inhibits deep convection. And of course, there's plenty of freshwater in the Arctic, in many forms: Greenland ice sheet, Arctic rivers, Pacific inflow, precipitation, both gyre and sea ice. Some are sources, some are reservoirs that get filled and replenished, for instance, the Beaufort gyre. But they're all have the potential to impact AMOC through this increasing the stratification in the subpolar North Atlantic or the Northern Sea. And many of these aspects, the sources are bound to change due to anthropogenic forcing. For instance, some of the gateway transports have already been identified as being changed due to anthropogenic forcing, for instance, by Alex John and Rory Leah and Tom. I'll go through three examples in which three studies, basically mentioned three studies that look at the impact of these freshwater inputs on the strength of the AMOC, or the stratification in the subpolar North Atlantic. Burning it all looked at the Greenland freshwater input and the impacts on the AMOC in an eddy resolving ocean model. So they applied a kind of realistic gradual increase of about 0.5 millistrators per year, which is was inferred from estimates of the mass balance of the Greenland ice sheet, and that's indicated here in this steel line. And this would lead to a 0.02 shredder input in the year 2019. So this plot shows the AMOC response in a control integration and an integration where this freshwater flux was applied. And they argue that there's not really a big difference yet after these 20 years of this applying this freshwater flux, so 30 years of applying this freshwater flux. The difference between these AMOC lines is not very large, especially compared with the internal variability. And they basically argue that the freshwater anomaly has not yet had a significant impact on the AMOC. But also they showed this simulation where they suddenly applied this 0.1 shredder of freshwater around Greenland, and you see a very significant decline in the AMOC in a very short amount of time. Beaufort gyre variability. Beaufort gyre is known to accumulate water and release water on a multi-decadal timescales. In this paper by Zhang et al., we looked at the impacts of that on the subpolar North Atlantic, and we found that the difference between a fast release and a fast accumulation phase of the Beaufort gyre had about 0.2 to 0.4 PSU impact on the surface salinities in the latter Earth. So this also has potential to impact the AMOC. Finally, the impact of sea ice loss was studied by Sevelik and Alexei Verov's group in particular. In this paper, they calculated the adjoint sensitivity of the AMOC with respect to surface buoyancy fluxes. And they found that on multi-decadal timescales, the AMOC is most sensitive to buoyancy fluxes anomalies in the Arctic. And the pattern that is shown here is the pattern that is most influential when applied over a timescale of 50 years. So they deduced from that the AMOC is sensitive to sea ice loss, and that sea ice loss weakens the AMOC due to the fact that the Arctic Ocean is allowed to absorb more heat. In later studies, they pointed to also to a more active role of the freshwater flux implied by changes in the sea ice cycle. All right, so to summarize, the AMOC is only partly responsible for ocean heat transport variability into the Arctic. It is also important roles for regional winds and gyre dynamics, the polar gyre dynamics. And there are many ways in which the Arctic can impact the AMOC. That's for water mass transformations, for instance, or through these different sources and reservoirs of fresh water. And also the link between the Arctic and the AMOC is projected to strengthen, and that's despite the weakening of the AMOC, either observed or projected. And this is, of course, concerning given the large changes that are taking place in the Arctic in the future. With that, I'd like to.
Thank you. time for one. And if you're online, use the raise your hand button, or you can type it into the chat. I don't see any questions, so let's move on to our next speaker.
Okay, Leifang Leah, we talk about century-long trends in area.
Thank you, everyone. Today I'm going to be presenting my research with Dr. Susan Lozier of Lee, and it is currently undertaken by my PhD student, Leah at Penn State University. So the motivation of this study is definitely the non-uniform temperature response to anthropogenic forcing. We would expect a temperature to increase everywhere with the increasing greenhouse gases, but the subpolar North Atlantic obviously turned out to be an outlier where temperature is actually cooling in the past century. I guess previously people call it the North Atlantic warming hole, but if we look at the temperature record, it is an absolute cooling. So we think it is more appropriate to call it the cold blob. So the presence of this cold blob has been hypothesized as an evidence of the slowdown of the AMOC circulation. So with the decreased northward heat transport, we expect the subpolar North Atlantic to experience a cooling effect. And we would expect the cooling to spread into the entire subpolar North Atlantic basin. However, if we pull out the temperature record, we actually find the cooling is concentrated over the eastern portion of the subpolar North Atlantic, basically the Arminger Sea, but the Labrador Sea ocean basin is experiencing accelerated warming. So it is in contrast with the AMOC paradigm, which is expect a basin-wide cooling. So that really motivates us to look at whether there are other processes contributing to the North Atlantic cold blob. And there are also modeling results, which my student picked one out of the climate models in the historical simulation, which indeed simulated a North Atlantic cold blob, and she analyzed the portion of the SSTA trend explained by the AMOC versus unexplained by the AMOC. And as we can see, the AMOC slowdown only explains a marginal portion of the SST trend, about at most 20%. So still a large portion of the variance is unexplained. And we are asking the question, what else of the processes are contributing? And Ife took a look at the circulation over the North Atlantic Ocean, and she performed a EOF analysis to the sea level pressure, and we get the first three dominant patterns. And what we can see here is from the time series, the first dominant mode, the NAO, it shows a significant increasing trend towards the positive phase. So this more positive NAO is going to lead to a intensified storminess over the subpolar North Atlantic as the jet stream intensifies and the barochronicity increases. So it promotes more passage of the storm and stronger storminess over the subpolar North Atlantic. So with a stronger storm passing by, we would expect it tend to disturb the ocean surface even more, promoting the heat loss, provides a potential cooling effect. And this cooling effect can be quantified using an idealized two-box model by first assuming there's no oceanic heat transport. So in this two-box model, we divide the ocean into two layers, a mixed layer and the subsurface ocean. So the temperature variation in the mixed layer, equivalent to the sea surface temperature, is forced by two mechanisms, the air-sea heat flux and the thermocoupling between the surface and the subsurface layer. So here, the QNet representing the air-sea heat flux is both a damping mechanism and a forcing mechanism. I call it damping mechanism because the turbulent heat flux is dependent on existing temperature. So if we decompose the QNet, it can be written out as a damping process and a forcing due to the atmospheric process. And we also have a thermocoupling term describing the heat exchange between the mixed layer and the subsurface layer. So if we write out these four terms correctly, the first two terms is going to quantify the atmospheric contribution, and I call it a direct atmospheric contribution. And the second two terms, they are also in response to atmospheric forcing because the wind forcing is going to induce convection, so it leads to a difference in the thermocoupling between the surface and subsurface ocean. So I call these two terms indirect forcing. And in our idealized experiment, we sequentially adding these four terms into the idealized model. So if we only consider the atmospheric white noise, then the heat balance model is going to be simplified as a Huffman model. And we parameterize the atmospheric forcing as a white noise. So this is our result showing the probability distribution of the centennial SSTA trend of the subpolar North Atlantic. As we can see, since we are adding a zero-centered white noise, so the resultant SSTA trend is centered at zero. But we also observe a wide distribution of the SSTA trend from the white noise. And actually, the white noise alone has about 17% of the chance to match the observed SSTA trend. So that gives us a hint there's a large uncertainty when we are trying to attributing the SSTA trend in the subpolar North Atlantic to a specific magnitude. But at the same time, as we observed those atmospheric changes, there's also a trend in the atmospheric component of the heat flux, which is a forcing term. And as we can see, according to the three reanalysis data sets, there is about 10 watts per meter square per century cooling trend applied by the atmosphere. So if we take that into account, the model simulated SSTA trend match about 50% of the observation if we consider it as an annual mean. But at the same time, once we are promoting stronger heat loss from the ocean surface, we would expect the ocean to respond as well. So we use a PWP model to derive the ocean convection in response to the heat flux change induced by the atmosphere. So if we consider that effect into the idealized model, and we can see now the idealized model quantification matches observation pretty well. It explains about 92% of the total observed SSTA trend. So this is a domain average. If we expand the simulation into the entire subpolar North Atlantic basin, we get a similar result to the domain average. So the direct forcing generates about 0.2 watts per meter square, 0.2 Kelvin per century cooling, which is about half of the observation. And if we add the indirect effect into the model simulation, it quite well matches the observation. So from our idealized model, we conclude even without a explicit resolving of the AMOC slowdown, the atmosphere alone can pretty much explain the observed code block. So back to the AMOC question, does the AMOC indeed slow down in the past century? And according to the current CNIP 6 models, there seems no agreement among the models whether the AMOC slowed down or not. So if they analyze the 18 of the CNIP 6 model, what she finds is that the model mean and the model median can go either above or below the zero line. So saying there's no model agreement. Okay, so overall, from our study, we figured out that the North Atlantic code block can be generated without an explicit role of the AMOC slowdown. And we propose with the increased storminess of the subpolar North Atlantic, it effectively disturbs the ocean surface, promotes heat loss, and contributes to a atmospherically forced code block. I'll stop here and thank you for your attention.
All right, we have a question in the audience from Chris Paikuch.
Laifang, nice to talk.
Hello, have the mic.
Oh, there we go. Thanks, Mike, for the mic. Laifang, nice to talk. Just to make sure I understand, so the last slide said that the Atmos trend term explains about half of the magnitude of that cooling, and then the indirect terms, the other half.
Yes.
And maybe I misunderstood, but couldn't it be that that atmospheric trend term that you're taking as a given was forced by AMOC? You drive a decline in the AMOC, that gives you sort of the warming, well, that's going to drive a heat flux, right? And so maybe that's embedded in the product you're using that you're calling Atmos trend. So there could be an AMOC influence, it's just sort of hidden the way you define your terms.
Yeah, I totally agree. So that's why we are very careful when we make a conclusion. We say it is without an explicit role of the AMOC. So possibly we are still diagnosing the atmospheric component of the forcing term. And it looks like, I think in Yifei's poster presentation, she figured out it's more like a radiative flux providing a most significant cooling effect. So could be some linkage with the AMOC, but we are unsure like how that works.
Thank you.
Thank you.
Any other questions? One in the audience?
Maybe I can, yeah.
That was a great talk, very interesting. I'm curious about the spatial variability. You showed, at least in one of the database plots, that you had the cooling in the Erminger Sea, but then you had a warm anomaly or warming trend, Labrador Sea. And so why would these be different? Is there some explanation why we wouldn't expect maybe a similar atmospheric forcing of increased storminess over the Labrador Sea too?
Yeah, that's a great question, and I think Susan and I, we explored a little bit in the PWP model. It looks like for the Labrador Sea, because it's less stratified compared to the Erminger Sea, so the convection is very easy to onset, and blowing even stronger wind does not make any difference for the probability of the convection to onset. So it looks like then the Labrador Sea ocean basin is more likely to follow the greenhouse gas induced warming trend.
Like also the storminess trend misses the Labrador.
Yeah, so
Susan, could you repeat that?
Right here. I'm just pointing out that the storminess trend is centered, or if you look at that, it doesn't really cover the Labrador like it does the other parts of the North Atlantic. So in addition to talking about the sensitivity and convection, the difference between Erminger and Labrador, I think this also plays a role.
yes, thank you.
All right, one more question.
So it looks like you have knobs in your model, like H1 and alpha. So have you looked at the sensitivity of the trend to that factors?
Yeah, we did check the dependence on the mixed layer depth and also alpha. And those terms comes into the e-folding time scale. So, and then there's also some nonlinearity in the parameter space. So once in the subpolar North Atlantic, because the mixed layer depth is deep enough and the e-folding time scale is long enough, then you are further perturbing these parameters, does not generate a significant impact in the SST response. But if you perturb the Q animal, it's going to generate a large SST response. I think Susan and I, we discussed a little bit in our AMV paper. We can talk later. Thank you.
Okay, our last talk before the discussion session is virtual. Andreas Schmittner.
All right, Andreas, if you want to share your screen, we'll pull you up into our screen.
Can you see my screen?
Yes,
Can you hear me?
yes, we can hear you and see your screen.
All right, thank you. All right. Too bad I can't be with you all this morning, but I'm trying to switch gears a little bit here, I guess, and talk a little bit about paleo and constraints, particularly from sediment data that we have on past changes in AMOC. And specifically, I'll be talking about carbon isotope constraints and the specific AMOC properties I'll be talking about is the strength and the depth of the AMOC. And this work was done mostly by Juan Muglia, who is in Argentina currently, and it was supported by NSF. So the motivation really is how well do carbon isotopes, and when I say carbon isotopes here, I mean C13 and radiocarbon, how well do those constrain AMOC properties in general, and AMOC strength and AMOC depth specifically. And the results of this paper were published in quaternary science reviews. In the upper right, you can see the title and the details there if you're interested in reading some about it. So we really were interested in separating the effects of AMOC strength and AMOC depth. So the idea is to use equilibrium simulations with an isotope-enabled model and filling out the AMOC depth, AMOC strength phase space, if you will, and then comparing those model simulated data with sediment data from the last glacial maximum, or LGM. The model that we're using is the Oregon State University version of the University of Victoria climate model. We call it OSU-UVic. It's a coarse resolution ocean general circulation model, and it has a simple one-layer energy balance atmosphere. The ocean is coupled to a biogeochemistry and isotope model that we call MOBI, and that includes process-based cycling of C13 and radiocarbon. We use standard last glacial maximum boundary conditions such as lower CO2, changes in orbital parameters, and imposed ice sheets. And then in order to vary the AMOC independently in depth and strength, we impose freshwater perturbations both in the Southern Ocean and in the North Atlantic. And I'll show you in a second how that fills in this two-dimensional AMOC depth, AMOC strength phase space. But before I go there, just want to talk shortly about the sediment data that we're using to compare the model with. So we're using the C13 compilation from Peterson et al. 2014 that has more than 400 data points. But as you can see from the map, they are mostly in the Atlantic, and the data density in the Pacific and Indian Ocean is less. So data are more sparse there. The radiocarbon data come from Skinner compilation. There's less data overall, roughly about 250, but they're more equally distributed between the ocean basins. So there's quite a lot of data, and now here is how, a diagram that illustrates how we fill in this two-dimensional AMOC depth, AMOC strength phase space. So on the horizontal axis, AMOC strength is depicted as the AMOC at 25 north. And then on the vertical axis, we have AMOC depth in meters. So you can see the diagonal row of points there. Those are model results that show the correlation coefficient R with the data of the C13, so the C13 isotopes. And we have generated these model simulations by increasing the southern hemisphere moisture flux, the meridional moisture flux. So as you increase the meridional moisture flux in the atmosphere, that freshens Antarctic bottom water and increases the AMOC depth and the AMOC strength. And you can see AMOC depth and AMOC strength in this series of experiments is correlated. If we, for example, would identify now the highest correlation coefficients are in these darker orange colors, which are about between 9 and 10 spherotrops and around 2,300 meters depth. As the best fitting models, we would not be able to say if the AMOC depth or AMOC strength determines this fit. So therefore, we have performed additional simulations where we decreased
All right, it looks like we lost Andreas. We're gonna try to get a call in. Or is it kind of bigger? I guess while we wait for Andreas to come back, does anyone have any questions for any of the previous speakers that have gone today?
All right, I have a question for Leifang, or really anybody. So we've got these two explanations for the warming cold or the cold blob. One argues that it's a weaker AMOC, and the other one says the atmospheric buoyancy force is stronger, so it's colder. But we tend to think the AMOC is forced by buoyancy loss to high latitudes, so are those consistent? Weaker AMOC makes it colder, a stronger force makes it colder. Any thoughts, comments?
It's a couple of systems. Is that brilliant?
Well, it's non-linear too, that's probably covered a lot.
I'll just say that I think, in all seriousness, we can't discount ocean dynamics completely or the atmospheric dynamics. You know, I think in my decades in this, I think we collectively, you know, the community would argue, the AMOC community would argue for an AMOC only, you know, explanation for this. But it's clear based on a number of studies that there's clearly a role for atmospheric forcing as well. And that coupling is clearly important to highlight. I'm really not saying anything original. I'm handing this back to you quickly.
I guess my question wasn't so much which one's right. It's, can we do much about dynamics? Let's say both frameworks are correct. Can we deduce much about dynamics from the observation that we have this gold patch? If seemingly one mechanism argues for a stronger AMOC and the other one argues for a weaker AMOC, and they have the same symptoms. I'm really just trying to kill time until we get up there.
Temperature alone can't be the diagnosis. That's what yeah.
All right, Joe?
Yeah, I got a question. There we go. Okay, so I have I guess it's the same question that Fiamma was wondering about, and it follows this one too. So what determines the structure of it? Why is it so localized? You know, if it is atmospheric forcing, you'd expect something to be much broader across the polar gyre. If it was AMOC, you'd expect to see hints of cooling in other places as well. Why is it so localized on the place? What's the thinking about that?
I just want to add something that came to my mind too. Was I want, before we get into what's causing it, I think the question of what's robust in the data too is because I wasn't sure when we looked at that different spatial pattern if it was the same period of time that we were looking at the trends. But that would be another question just to add on before we start jumping into the mechanisms.
Annalisa, I see you have your hand raised.
Yes, I was just trying to answer, I think it's Joe who commented on the localized thing. There are mechanisms by which you can essentially have a response of a terrain wave from the tropics that will do exactly that and really just generate a cooling on that side of the Labrador Sea. We had an old paper in 2004. It was not looking at that problem at all. I mean, it was really looking at the NAO modulation. But if you do the regression, it's exactly that pattern. And it's essentially a wave train that hits you pretty much right there and is really atmospheric. Then of course, we'll modulate the strength of the gyre and will eventually modulate AMOC possibly and be modulated by it. But it's not impossible to get something that really localized just on the atmospheric side. And Fedorov, I kind of have looked at that again and more recently, a couple of years ago, in one of the Nature family publications with a student of him as well. I mean, we looked at the same problem for the 90s, and it was there. It was the same pattern, the same strength, pretty much.
So I've got a question that follows everyone, and Lisa's and Chris and Fiamma's and Joe's. And I'll give Susan's caveat that maybe I just don't know the answer here. I think Chris's question, Chris Little, his question is a really good one in terms of how robust these features are. We've been talking about the physics, but I'm unaware of anyone who's really interrogated. I mean, we're all using these sort of gridded SST products, right? What's the data availability going back to the beginning of the 20th century? How much of this spatial structure isn't physical, but how much of it is just whatever infilling algorithm is used by AdISST or whatever the product that we're taking. And we can't just compare 3 different SST products because they're all based on the same data, maybe make similar assumptions. I think that, an interrogation of where the data are, when the data are, and how that might influence our inferences, I think is just as important as asking these physics questions.
Alexei, I think you have your hand raised. Alexei, can you hear us?
Okay, sorry. Yeah, I hear. Yeah, I just wanted to echo what Annalisa said. And an interesting part is that you can cause the same structure of a warming hole in the subpolar North Atlantic or south of Greenland by weakening of AMOC or by the atmospheric processes. And it's actually very hard to distinguish what causes it, the atmosphere versus the ocean. In a idealized modeling framework, you can do it separately, but the structure of a warming hole, it's still more or less the same. And it's basically because you have a budget, a heat budget for this region. And you can change the heat budget of this region by different means, from the atmosphere or from the ocean. So that was my comment.
Okay. Yeah, just wondering, Laifang, if you could look into the salinity budget, because it's AMOC, that it changed not only heat advection, but also salt. But if you just use the atmosphere heat flux change, then the influence would be different in salinity and temperature.
Microphone. Yeah.
For the salinity change, should also the T-E pattern related to the atmosphere also imprint in the salinity signature as well, which like creating something similar to the SST pattern? Or would we expect those patterns to be spatially different? That's my question.
It should be apparent that we've lost Andreas and we've moved into the discussion session. So this is really kind of an open format. We're hoping to talk about all the talks this morning, either technical details or big picture issues, with the notion of talk about unsolved problems, talk about where we might go in the future, what are the big questions that the community should be looking at next. And you're, of course, welcome to keep talking about you still have comments to make about that.
We have a question from Martha online.
Hi, thank you so much for letting us virtual people participate as well. My comment had to do with Laifang's talk, kind of continuing this discussion. So I really enjoyed the talk. Thanks, Laifang. I was going to point out that ocean processes doesn't necessarily have to be the AMOC, and echoing what Alexi said, is hard to separate the atmosphere and the ocean. It's very hard to separate the role of different ocean processes in determining SST variability. But one thing that I have found is this region that has, in this kind of cold blob warming hole region, the predictability of SST is large, and it's like larger than you'd expect from the null hypothesis. So if you subtract the predictability from the fully coupled, the slab ocean model from the fully coupled model, you find a big positive blob here. So that's one kind of signature that ocean dynamics might be important. Another aspect is that reemergence is actually really important in this region. So you can enhance the predictability in this region by reemerging SST anomalies. And that's actually not true in the Labrador Sea. The Labrador Sea has very low predictability of SST. So there's a few thoughts about connecting these various aspects to understand why you might have a warming hole in that region. It's not an answer, obviously, but it's more to the complexity of the problem. So.
Any more thoughts on kind of big picture issues for the community? How about the Atlantification of the Arctic, or the flow of warm water into the Arctic? Wilbert talked a little bit about the Arctic polar connection. I guess a question to the modeling community: are climate models sufficiently realistic in terms of sea ice and freshwater budgets and boundary currents and so on? Are they sufficiently realistic to begin to address that issue? And for the observational community, what would we need to measure to try to understand the physics behind that connection, what's driving lateral water into the Arctic? And we see it's in there, but I don't think we really understand what controls that flux. And of course, we can't predict how it might change if we don't understand how it is now. So any comments on that connection between the polar and the Arctic?
ocean dynamics, the Gokhan really is the bridge between Greenland, Iceland, and Scotland. I mean, once the Atlantic water gets into the North Sea, it's easy to get in the Arctic Ocean because the Chomiak and differentiated speed. What's really difficult is the exchange between the North Sea and North Atlantic Ocean because the still depth is so shallow. Demonstrates only like 640 meters. And Faroe and Iceland is only 400 meters. And between Faroe and Scotland is only 800 meters. So in the large scale, I mean, Chomiak can't be blocked by the ridge. I think that's the job.
The geostrophic contour is deeper than the sill depth. Of course, you still have them run along the boundary. The boundary effects are heavy up there. But why has it been changing? I guess that's a related question. Susan, you were about to say something. I'm going to hold you to it.
No, it's actually a question for everybody else. Is the change due to the temperature variability or current variability? I don't know. Somebody in this room.
I can't follow all the discussions going on, but one comment that I might make with respect to Will's talk is that there's a large amount of water that goes into the Barents Sea. I think he showed something like 4 centimeters. Some of that will go north into the Arctic, east of Svalbard, and so forth. But some of that gets cooled and runs back out through the Bear Island Channel. And at that point, the water is much spicier. So there's a big overturning process taking place right there in the Barents Sea.
So I directed a question toward modeling for, I'm going to look at Gokhan here. So I'd say something, how do the models do look up here? I know we talked a little bit about the difference in variability in terms of east and west OSNAP. How about further north?
I'm not aware of any one more intercovariance studies, CWIP6 style, looking at the transports. I know that the Rasmussen team has done an analysis of the heat flow flux conversions into the Arctic and found a very strong relationship with the trends of sea ice in that model ensemble, basically. But with respect to the Arctic and like the AMOC, I think the trend is that the multi-model averages are fine, but there's incredibly large spread still that is carried over from generation to generation of CMIP 3, CMIP 5, CMIP 6.
From the modeling world, I'm aware of at least 2 studies. One was looking into the representation of hydrographic properties. Hydrographic properties in OMIT, that's forced ocean sea ice models. And then there's actually, I believe, a study looking at the coupled simulations from CMIP 5, again looking at temperature salinity profiles in the Arctic representation in the model. And there is a huge range in terms of temperature and salinity biases in the Arctic in terms of their vertical profiles. They are they are biased compared to limited observations. The problem is that if it's not just the transport getting the right water mass properties into the Arctic, but where those water masses are also modified within the ocean or within the Arctic basin makes a big difference. For example, if the formation of some of those water masses are occurring in the Kara Sea or Barents Sea and all that stuff, and it depends, and it seems to be strongly dependent on the representation of the shells, bottom topography. In the models, we don't have necessarily the right surface fluxes. We don't have the proper representation of the bottom topography. So we don't necessarily have the modified flows going into the Arctic to determine the water mass properties. And then in turn, if you have too much or too warm water at shallow depths compared to observations, then that makes a a huge difference, because if you have a warm bias, if suddenly that bias is eliminated or somehow that warm water mass is released to the surface, then it's going to create melting sea ice. And that is going to change any kind of future projections. So that's an extra level of complexity that we need to deal with, extra heat floating around at 500, 400 meter depth in the Arctic Ocean.
I saw a comment by Laura online. Did you want to unmute and make that comment?
I think there are a few people saying that it's really difficult for the remote people to follow what's going on.
Yeah, so for the in-person folks, if you could say your name before you make a comment, that way the virtual folks know who's making the comment.
Sorry, did you want, who's, I don't see.
Laura Jackson, I think, wants to say something. Laura, are you there?
Can you go to the chat? Bottom right here. Is lost there. Yeah. 10%.
To unmute someone.
Andreas is back if you want to complete his talk or not.
We should be fair, let it finish. How do we get him back up there?
Andreas, can you hear us? I think Mike Paul wants you to finish your talk.
I think we should take a vote.
Clarification, everyone wants you to finish your talk.
Thank you. I don't know when I cut out, though.
It's on the summary slide.
The summary slide?
No, it's just going.
The one before the summary slide.
So you'll need to reshare your screen.
Okay. Was that the slide where you cut out? Where I cut out? This one?
Number.
We're thinking
Is
number 7 or 6.
7 or 6? This one?
Previous one.
This one? Okay.
No, keep going.
Keep going.
Okay, so we were filling in this two-dimensional phase space here with these model simulations, and in addition to changing the southern ocean buoyancy fluxes, which generated this diagonal here, we changed North Atlantic freshwater flux, which then impacts only the AMOC strength, so it moves these points here on the horizontal without changing AMOC depth. So this way we were able to fill in this two-dimensional space. And as you can see already from this initial diagram here, which shows the correlation coefficients for the C13 data, that the isolines, some of the isolines are indicated here, they are all horizontal, pretty horizontal. So they indicate that these data essentially constrain AMOC depth, not AMOC strength. So for example, for an AMOC depth of 2,400 meters or so, the AMOC strength varies from 9 to 17 spherodrops, and the data do not provide strong strong differences between these simulations. So this is the correlation coefficients for C13. We also looked at a different model. This is the same diagram here again. We looked at the root mean squared error as another model data fit metric or misfit metric, which is shown in this diagram here. And again, you see something similar, horizontal isolines indicating that the AMOC depth is well constrained by these data, but AMOC strength is not well constrained by these data. And I also wanted to mention that these errors here are normalized by the estimated model and combined data errors from the pre-industrial. And so values of around 1 indicate consistency between the models and the data. And you can see that essentially these shallow AMOC depths are all consistent, more or less the same, consistent with the data, then no matter what their AMOC strength is. Okay, so we had looked at different ocean basins, the Atlantic in the center panels and the Pacific, Indian Pacific in the bottom panels. And there you can see that the Atlantic essentially dominates the global distribution, which is not surprising because the Atlantic had most of the data. The Indo-Pacific slightly seems to prefer weaker AMOCs. We did the same for radiocarbon. This is shown here now in this graph. And if you just look at the upper left, this is the global correlation coefficient of the global data. There's not much difference, so indicating that the in terms of RMS error, radiocarbon is not very sensitive to either AMOC depth and AMOC strength. But in the root mean squared error, we can see some sensitivity, which would favor these intermediate depth values. But again, you can see quite horizontal isolines indicating, again, that AMOC strength is not well constrained by these data. And Juan did go a little bit more into depth to analyze what determines the radiocarbon fit to the data. And this is shown in the upper right here, which just shows the whole ocean difference between the model and the data of the radiocarbon, where again, you can see it is strongly influenced by AMOC depth, but not by AMOC strength. And we could identify that the whole ocean radiocarbon value depends mostly on the Southern Ocean reservoir age, which is shown in these left panels. And on the top, we have it, Southern Ocean reservoir age shown as a function of AMOC strength. And there you can see quite a large scatter. And in the bottom, you have it as a function of AMOC depth, which is a much better fit. So again, illustrating how AMOC depth influences radiocarbon distributions through the Southern Ocean reservoir age. Are you still there? Okay.
Yes.
Okay, good. And here a little bit more on the patterns. Why do these isotopes constrain AMOC depth better than AMOC strength? The top 4 panels that are surrounded by the green frame show the effect of AMOC strengthening on C13 on the left and radiocarbon on the right, for the Atlantic in the top and Indian Pacific in the bottom. And the lower 4 panels surrounded by the pink frame indicate the effects of AMOC deepening on these isotopes. And there you can see already there's a big signal in the North Atlantic, in the deep North Atlantic, for AMOC deepening. So that increases the C13 by more than 1 per mil, and also reduces the radiocarbon age by more than 700 radiocarbon years. So this is a large signal there, which you cannot see if, for the strengthening case. So AMOC strengthening just has much smaller amplitude response in terms of these isotopes, even in the Atlantic. So this is essentially explaining why the AMOC deepening is constrained much better by the data than AMOC strengthening. And that already brings me to the conclusion. So the carbon isotopes provide strong constraints on AMOC depth, but not on AMOC strength. AMOC depth was at the LGM was between about 2 and 2.5 kilometers, which is about half a kilometer or about 1,000 meters shallower than today. And whereas the AMOC strength cannot be constrained between about a range of 8 and 17 Sverdrups, which are all similarly consistent with the data. I also want to mention that our results are consistent with the recently published study by Gu et al., who used CESM. And there seems to be a predicament, but I think for future work, we want to try additional paleo constraints, such as neodymium isotopes and productinium-thorium ratios, which may be more sensitive to AMOC strength changes, because
Andreas, we may have lost you.
Yep.
Yeah. You still see your slides at least. Great, should we go directly into discussion again? Discussion part 2?
I have a question for Andreas, but I can ask you.
Well, just give him a couple minutes to see if he gets back online. Executive decision here, we're moving on. So we have another 20 minutes for discussion.
Could you stand up at the podium and then we can run the background to the people that are looking?
Sorry if I'm what they got to look at. So, okay, let's continue the discussion. It doesn't need to be about the northward penetration of Atlantic waters. It can be about anything that's on your mind, other than lunch. So, to the observational community then, I've put things on the modeling guys a little bit, so now the observational community. What things are still outstanding issues, not other than monitoring for low frequency variability, but what kinds of things do you think we really need to observe that will help us understand the mechanisms of AMOC better?
I could suggest that a major question is, as the NAO varies, and perhaps on longer time scales too, what is it that dictates whether water out of the Labrador Sea will primarily go south versus go east?
Okay, that's a good question. How would we observe? What do we need to know? I mean, we can describe it, but how do we understand?
We have a question online. I think we have a question online, if you want to unmute.
Hi, how are you? I didn't know if you were speaking to me. So I think one of the things that we're grappling with is reconciling the differences between the different observational approaches and what they tell us about AMOC variability on different timescales. And the other thing is, you know, as you heard from some of the talks today, there's a lot of interior pathways. And so I think in the South Atlantic, we also have interior pathways, and trying to understand, you know, what happens to North Atlantic deep water as it's making its way southward and maybe moving towards the interior partly, trying to understand those pathways, I think would be great to have more observations of.
So maybe Eleanor and others can chime in as well. As part of our AMOC metrics project, that's when we've looked at rapid and move arrays, and we are looking at SAMBA as well. But I'm sort of preaching to the choir again. What you do with your reference velocity at the bottom matters a lot, and what you use to compensate for the zero net volume transport at rapid matters as well. And based on the SAMBA analysis, it looks like how many moorings that you have in the water can impact the variability that you get out of the system. So that's another thing that is important. And I think all of these observational programs are realizing that the bottom reference velocity assumptions need to be perhaps revisited in a careful, revisited, I guess.
Not all of them use reference.
Not all of them use reference. Yes, OSNAP is okay, I think.
Hey, Gokhan, while you have the microphone, you mentioned you had a question for Andreas.
Well, yeah, I was, when Andreas Schmittner, he is back online, indicated that paleo AMOC perhaps was shallower in
sort of modern world, we tend to associate the depth of the AMOC overturning cell associated with the North Atlantic seawater with the strength of the overflows. So does it mean also that in the past, with the shallower AMOC, were the overflows shut down or they were small? What is the connection, I guess, with the depth of the overflow, with the depth of the North Atlantic deep water versus the overflow strength or its density properties in the past?
Well, I don't think that we know much about the overflows in the glacial, for example, in the past. But in the model, we modified the AMOC depth, particularly by changing southern ocean buoyancy fluxes. So that affects Antarctic bottom water and therefore affects the AMOC depth. So, you know, it can be forced from the south too, particularly for equilibrium long-term simulations in the model. Yeah, so I don't think I can say much about the overflows. I don't think we know much about that. Maybe somebody else like Delia Oppo can chime in here.
I also see a lot of action going on in the chat right now between Eleanor Ranellis and I think I'm missing one more, Matias. You guys want to unmute and possibly turn on your camera if you feel comfortable.
Hold on, before we move on, Tom Rossby, I think had a comment on the discussion we just had. Tom?
Yes. The water that is produced in the subpolar North Atlantic, that convection doesn't reach any deeper than about 2 kilometers, maybe a little bit more. The reason we say that that cell reaches deeper today is because we have a lot of entrainment of intermediate water by the deep water overflow. So I'm not quite convinced, but we didn't have that during glacial times because there was no overflow. The deeper part of the Atlantic was filled with southern ocean water. So I'm not quite persuaded that the upper cell, that is the intermediate cell, the intermediate water production, is actually showing that much. It appears to be showing because we have entrainment into deeper water, but not because of production of intermediate water.
Sure, go ahead. Then we have some online.
No, I know. I was not that one, the online one. I'm glad that I actually instigated all the discussion online. I was just telling things on purpose to instigate this discussion.
Alexei, do you want to say something?
Yeah, actually, I had a question to Andreas, if we still can ask him a question. Andreas, are you still there?
Yes, I can hear you.
Okay, great. So I have a question about your computation. So each point of on your plot is a model run, right?
Right.
So especially with with AMOC depth, you really need a very long time, sometimes thousands and thousands of years, to get that equilibrated.
Mm-hmm.
So how did you guys solve this problem?
We run it to equilibrium. The model is really efficient, so we run it for 5,000 years, and we need that long integration times anyway to get the isotopes to equilibrium. So they all run for 5,000 years.
And so you think 5,000 years is enough in your case?
Mm-hmm. Yes.
Okay, thank you.
Eleanor, do you have a comment?
Yeah, this was just in response to Gokhan, I don't know if it was a question, the comment about the geostrophic reference levels being still an issue for the observing arrays. And so I was just commenting that we are putting in some drift-free bottom pressure sensors at Rapid. These are not actually drift-free, they're sort of self-correcting or self-calibrating drift. They measure their own drift to try and do a reference level a little bit more directly. And Stuart Cunningham is putting in a couple at OSNAP, and it looks like Matthias may or may not, they're working on getting them for 16 North as well. And I know there are other folks here, Chris Pykuch and some other folks that I see on the participants that were also at a meeting between geodesists and oceanographers and trying to use these sensors a little bit more broadly. Yeah, so that was just in response to Gokhan.
Okay, Susan's got a question, and then Uber.
It's actually just a comment following up on this, and Gokhan and I talked about this earlier. I think an excellent collaboration between those of us who've been working on observations and the modelers is to, now that we have several years, if not some decades, of these time series at various latitudes, is to implement, the Aussies at all of these, different latitudes, implement the observing systems, ground truth them with the observations that we have, and then just run them forward. I was really impressed with the work where you compare what's, the differences between, rapid and move, and we'd love to see that with OSNAP as well. As observations, we have to be completely open to the possibility that we are missing some of the variability or missing some of the mean, and it would be really interesting, to test that. I will say, however, I think it's naive to think that we can have the same observing elements at all latitudes. We just have different dynamics, we have different opportunities, we have to look for efficiencies. OSNAP in particular, has many different boundary arrays because of the many different subbases. Also, isn't a single overturning cell. So it's great to think that we can sort of standardize, but I think that's naive. But using the models to tell us what we're missing, and particularly using the models to tell us what coherence we have, would be really very useful.
Okay, Wilbert?
Can you hear me without Yeah, this is in response or addition to what Eleanor just said about the reference level topic. I think some of you may be aware that Janis Curling in our group, he had used bottom pressure from the GRACE project to reference our transport estimates, and he found that on long enough timescales, we get the same results whether we use an appropriate reference level or referencing it to bottom pressure from GRACE. So there's some independent confirmation on longer timescales.
Wilbert, did you comment?
Yeah, I was wondering about the dynamics of those interior pathways, and kind of following up on Ronel's question also. I mean, Eric Kosby had a really good paper a couple of years ago, the Miami group, about the pulling the North Atlantic deep water across the interior and South Atlantic underneath the pathway of the Agulhas current rings, basically. What is the dynamics of these interior pathways in the North Atlantic? And does it matter for the strength of the overturning circulation? Is it some kind of bottleneck? If I don't know how much is known about that, and if people know, then I'm very happy to hear it.
Is this a new hand of yours, Andrew?
I don't know how to interpret that question. Yes, I guess. Just following up on Susan's point, yeah, we will never observe things the same way because logistically it's not possible, resource-wise it's not possible, and sometimes the region lends itself better to different kinds of technology. But I think it will be good for the regions that we have multiple estimates from different platforms like hydrography, XBTs, altimetry, in situ synthesis, and moorings. We can try to understand the local reasons for why the variability differs between them. And it could be timescales resolved, spatial scales resolved. It could be methodology. It could be just physically we're observing slightly different things. And so I think as much as we can try to work to understand those differences, that would be great.
So Wilbert, because I'd like to comment on your question about things moving off the western boundary. I think we know about some mechanisms that can drive that. And just thinking in a linear world, everything's propagating westward. So it would be driven from the interior, right? If we have meridian and variable mixing, we know they can pull water off the western boundary. Ross waves would propagate at different phase speeds at different latitudes, will introduce a pressure signal on the western boundary, and that'll pull things off the boundary. That's more, I think, relevant for the variability, but the mixing could be relevant for the mean. And then, if we we go into the nonlinear world, of course, we can have a dashing off the western boundary and separate western boundary current. So I think seeing things come off the western boundary is maybe something to explain by dynamics going on in the interior. So that might focus us somewhere else.
If I could just add to that, not everything originates in the deep western boundary current, because there's a paper that Amy and Heather and I and Jim Drulin and Gian Xiaohao are working on, based on those snap flows. And there, the ISOW, a large fraction of that ISOW spreads from the Ison Basin southward. Like it never engages in what we think of as the traditional western boundary current, and it spreads along the eastern side of the Mid-Atlantic Ridge. So I also have this question, one, what are the dynamics that are producing that? But also, how do we reconcile our old view where we thought of the anomalies moving along the western boundary current that were getting us, basically that were related, let's say, to the deep water formation or volume anomalies, and that was getting us the signal when we have these interior pathways, and particularly with ISOW, it's quite evident. So I think that's very interesting. But past work has also shown that we can't take the volume formed in a particular year, whether it's Labrador seawater or northeast deep water, and trace that down, right? There's recirculation in the subpolar gyre. So we sort of have to accept there's sort of a disconnect between the particular waters that formed each year and what we see downstream and where. So, big question. Now that I have the microphone, can I just say something else? Because I do think, and I listed this on my questions that I don't know, I do think this community should take a serious pivot for trying to understand how the dynamics in the subpolar North Atlantic impact the uptake of anthropogenic CO2. So as much as I love the MOC, I think a focus on MHT and MFT, and then in particular the carbon question here in the modern world is really a pressing issue. And so we are, Jamie could talk about this, but I'm not going to do that and pass the microphone to her. But we just have we're starting to add, to the arrays some biogeochemical measurements that I think really would do well to accelerate that. I'm done.
More comments? Anybody online? Gokhan here?
Yeah, Jia Yin from small follow-up for students today. I mean, if you look at bottom layer, the eastern side of ocean ridge dynamics is no different from continental. I mean, it will be governed by, maybe the slope is different, but in terms of PV dynamics, it's the same. And there was a paper just a few months ago published by, I was also with a student, look into two reanalysis of that, just look at pathways. And you can see that the slope current on the eastern side of continental slope, following an OH contour, flowing southward, until the east and western basin, I mean, OH contour connected, then it will converge into the western mountain. Right. And I mean, the depth of this ocean ridge, becomes deeper, and also F becomes smaller. And the equator is doesn't matter. All should become converged. So at some point, it will converge into the western mountain.
That's tremendous.
Yeah.
Gokhan, you still have a comment?
Yeah, I was just going to bring up another thing. I don't think that has been discussed yet. It was too early for that discussion. Do we need, or what's the status of deep observations? When I say deep observations, below 2,000 meters depth, basin-wide Argo floats, perhaps. And I know that there is some work on that, but I'm not sure what the final status of that is. Because if you listen to reanalysis world, they would like to have deeper Argo data so that they can initialize better, or they can do reanalysis better, and that may help the predictions that the people are trying to do.
Any more comments? Over here.
Hello, Gail Forget from MIT. So I just as maybe a parallel comment to that, I think I don't hear a lot about cargo in the upper ocean, and I once upon a time did a PhD to show that it basically is an observing for system for the AMOC, in the way that you will have signatures through conservation principles of what you see in the AMOC that will be in the upper ocean, in fact, because of the coupling of the layers, because of the volume conservation and so on. So that's kind of my broad comment. I think more emphasis on looking at upper ocean data, a little bit in the sense of what was shown on the paleo stuff, but from the upper ocean hydrography perspective, I think there will be a lot to learn from that. So with the cargo data that exists,
OSNAP absolutely uses that Argo data. So, we have the boundary arrays, but in the interior, we are using the Argo data for our TNS, and actually we're going to try it soon to see if we can use it as a reference velocity as well. Currently use altimetry. The Argo is critical to our estimate, both across east and west.
Thank you.
Yeah, and just chiming in on that, as I mentioned, there's Argo altimetry hydrography products that are estimating the overturning circulation. So having deep Argo measurements can only make those products, even more, give more power to those products to have more hydrography below 2,000 meters.
Any final comments before we break?
What do you think the big question is, Mike?
Where to go for lunch?
I can answer that.
No, okay. Yeah, I tried to direct the conversation a little bit towards heat penetration NCAR. I spent some time trying to understand just the mean flux through Graham Strait with some theoretical models, and I had lots of theoretical models, and none of them agreed with numerical models, so I kind of never really got very far with that problem. So I think that's a big outstanding question.
So something must be wrong with theory then.
Only one thing? I'll take it. Okay, physical break. I think we meet back here at 2 o'clock.
Yeah, so we do have lunch catered for you guys, so it's a similar setup as breakfast. Out in the tent is where you can get it, and then you can spread around the premise. For the online folks, I'd like to do a group picture, so please stay on the line and turn on your cameras if you want to be included.
They catered lunch. I was thinking, oh, what a mess they're making when they're going down to
Yep. All right, so I see about 59 people online. Some of them are AV, so I'll need to do this in a couple batches. I wish I had 3 hands to take pictures, so it'll be not too graceful on my end. So.
I'm gonna hold something?
Yeah. Or do you want to just grab a screenshot?
Yeah.
Cool. And I'll let you have video. All right, so your hand's gonna help me. Hey, Renella, your hand is all raised. Do you want to take that off? There you go. All right, so everyone turn on your cameras, and I will do a countdown. We'll do a couple.
Full screen, or do you want me to grab like a second? Okay.
Yeah. All right, 3, 2, 1, smile. All right, we got one. So let's go over to the next group. All right, 3, 2, 1, smile. Perfect. Okay, so we have all your pictures. Thank you so much, and we will be back in 1.5 hours. We'll put it up there. Same lady. Thank you.
I'm gonna turn this off for now. Should we mute this for now?
¿Alguien se lo dicho al otro? Mira, Willy. No, ni camina ni pasa. Porque estoy pensando, mira, y encima ese enchufe va a amputar la pared. Está fino. ¿Qué pedo? Lo único es, ay, la opción que te queda corta por detrás. Hola, voy al parque. ¿Lo haces mejor? Voy al parque. Sí, dígame. Hola. Hola.
Hola. Adiós. Adiós.